Okay, so this presentation is for CDX, Chapter 62, gasoline fuel systems. So I'm not going to talk about diesel fuel systems here, really. It's really confined to gas. I have added things into this presentation from other resources I have, so this isn't strictly from CDX. I've also put a couple charts in here to kind of help break down, because there's a lot of terminology and nomenclature issues with fuel injection. When we get to EFI, PFI, SFI, and all these different acronyms, it becomes acronym soup. So I made a PowerPoint slide that I put in here to kind of break that down. I also included some diesel information in that. So this is our gasoline fuel system. So we've talked about the engine. We've talked about ignition. We finished up with ignition. And now we're getting into fuel. So in order for my engine to run, it needs three things. It needs compression, right? It needs, my engine needs to be able to compress and breathe. I need ignition and I need fuel. So those are the three legs of our stool. So anytime I have a vehicle that's running badly, at least one of those three legs is where my problem is. So when I diagnose a car that's running poorly, whether I have a code for it, like a misfire code, we're telling me a single cylinder is misfiring or multiple cylinders are misfiring, or if I'm working on an older vehicle that's just running rough, I have to look at all three legs of the stool. Is it ignition? Is it fuel? Is it compression? Now, once I have those things, they have to be there at the correct time. So one thing to keep in mind is that if I have something that's out of time, it has to either affect the whole engine, in the case of ignition timing, or camshaft timing if I only have one camshaft, or it has to affect the whole bank of an engine if it's a timing chain or timing belt, where it's going to affect all the cylinders on one bank of a V engine that would be affected by that timing chain or timing belt being off a tooth. So I wouldn't be diagnosing a single cylinder misfire and looking for a timing problem, because a timing problem is going to affect more than one cylinder. So if I have only one cylinder that's misfiring, I'm literally down to compression testing, both, cranking compression, running compression, all that stuff, ignition and fuel. Those are the three things I need for that cylinder to produce the power that's needed. So all of our diagnostics that we do, matter of fact, I have a class I'm doing end of this month that I'm studying for, is all about those three things, and about diagnosing them, and how to take a car with symptoms, customer says it runs bad, and how to figure out which leg of the stool has the problem quickly and efficiently by excluding the other two legs. And so that's something that even at a very high level of technician is something that technicians still struggle with, and technicians are still learning new ways of figuring out. So even though I'm breaking down all these systems and we're going to look at them, we'll talk about how each system can be tested and failed. If I have a vehicle that's running poorly, I need to figure out which of those systems it is. And that really gets to the next level at that point, when we start using some high level tests to differentiate what could be wrong. So my gasoline fuel system, now this module is broken into two parts, but only one chapter. So I have a PowerPoint for the fuel systems themselves. This is our mechanical components, basically, and how the mechanical components work, or electromechanical components work. The other PowerPoint presentation I have for this chapter is on the logic or the strategy that is used to control fuel going in the engine on a motor, and we call that fuel control. So we're going to look at that completely separate. So some of you may have heard terms like short-term fuel trim, long-term fuel trim, oxygen sensors. All that's going to be in the next PowerPoint presentation, still in this fuel module, but on how we control fuel going in the engine. So we're going to look at the different types of O2 sensors, how they work, how the computer works, how the programming in the computer actually works to control fuel, and put that all together. So we're going to learn about the mechanical, electromechanical function first, and then the logic second. Then we're going to start putting all those things together, looking at computers, computer function, and how we manage all those things. And then we're going to get into emissions and emission control systems, why we control emissions and emission function. So that's where we're going to end up in the class. So that's where we're going to be going in the next couple of weeks. So these are fun because this is where we really start putting, especially after this second half of this module, we really start putting pieces together and seeing where all the things you've learned going back to the first, second week, third week of sensors and circuits and all these other things, how we start putting all these pieces together in the next few modules. And so this is really kind of where it wraps everything up. So introduction, today's gasoline fuel systems must meter a precise amount of fuel into the engine under a wide range of operating conditions. Most important job of the fuel system is optimizing engine performance while keeping fuel consumption and emissions to a minimum. So low fuel consumption equals low emissions. However, I can have a car that gets good mileage, like a Volkswagen Bug, have horrible emissions. So I can get good mileage and still have high emissions. I can have low emissions when we look at it from a percentage standpoint or a parts per million standpoint, even on a vehicle that gets poor fuel economy. What we look at from the federal level is we look at emissions by weight. So we're actually measuring it in grams per mile. So they actually measure tons of pollution in the atmosphere and then extrapolate it down to the individual vehicle. So that's why fuel economy has such a big impact on emissions, is because they're looking at the emissions generated per mile traveled. So early EFI systems, sometimes called bug sprayers, were a throttle body injection system. Carburetors, introduction of electronic fuel injection, and then most early EFI systems used a throttle body system back in the 80s because it was an easy change from carburetor. So just some visuals here. We have a carburetor right here. This happens to be an aftermarket carburetor, not a factory carburetor. I wish they'd shown a factory one. This right here is a throttle body fuel injection. You can see it looks very similar in the housing, but it has two injectors that mount in it instead of the internals of a carburetor. Here is multi-port fuel injection, which was our next step. And this is direct fuel injection, where we're going to spray gasoline directly into the combustion chamber. This is my throttle body right here, but no fuel is in the throttle body. So this system here, multi-port and direct, will both still have a throttle body, but no fuel will be delivered through the throttle body, only air. In this system, air is going through the throttle body and mixing with the fuel that's being injected. And in this system, we'll see where air is used to create a Venturi effect to draw fuel out into the low pressure area and mix with the air. And we're going to look at how carburetors work. Pretty basic, but the main systems of a carburetor towards the end of this presentation. So I actually go to carburetors last. And because they do work very, very different than fuel injection systems. So we're going to go all through our fuel injection systems. Well, last year we put a carburetor on a vehicle in the US was 1994. Where we've had fuel injected vehicles going back to the 1960s. So most of the stuff you're going to work on is going to be fuel injected of one type or another. So as technology progressed, multi-port fuel injection, MPFI, multi-port fuel injection, or just PFI, port fuel injection, became prevalent. So multi-port fuel injection was actually around going back to the 60s. Where throttle body fuel injection, we saw it come out in the 70s and into the 80s. Predominantly by domestic manufacturers, but also some Asian manufacturers used it. The reason why throttle body injection was used on these vehicles, even though they had already invented port fuel injection, was cost. It was cheaper to produce, fewer parts, fewer injectors, less expensive computers. The other is it easily adapted to the existing engines we had. In other words, I could take the carburetor off and put a throttle body fuel injection system on with really minor changes to the vehicle. So it was very cost effective for manufacturers to do that. And that's why we saw that as really a transition going from the mid 70s with Cadillac in 1976 up through domestics, really, which continued on the Chevy trucks up into the early 90s. We saw throttle body injection. Multi-port fuel injection, as I said, has been around since the 60s. European vehicles have used multi-port injection forever. The 260Z Nissan sports car, that was 1974, if I remember correctly, either 74, 75, I think it was 70, it might have been 75, but it was fuel injection because the 240Z was carbureted and it was multi-port. Mercedes has been multi-port forever, BMW. So you see a lot of these, whereas some of the less expensive cars like Nissan Sentras were throttle body injection systems. A lot of domestic manufacturers were throttle body. Then you saw some higher end Buick, Cadillac, performance models of Ford and Lincoln going with multi-port. In the last 15 years, this has really moved now into gasoline direct injection. So this places fuel injectors directly in the cylinder head next to the spark plug. So with port fuel injection, we are going to inject fuel on the outside of the combustion chamber, on the back of the intake valve. On gasoline direct injection, we're now going to spray fuel directly into the combustion chamber. And that creates better fuel atomization, also better control. And keep in mind, gasoline cannot burn as a liquid. It can only burn in an atomized state or aerosol state. So it's the vapors of the gas that burn, not the liquid. So all of these systems are designed to try to atomize the fuel. Some of them don't do a very good job, like a carburetor. Throttle body injection didn't do a great job. Port fuel injection did a much better job, and gasoline direct injection does even better. An electronic control unit, ECU, commonly called an ECM, electronic control module, or PCM, powertrain control module, is needed to determine the proper quantity of fuel being injected. So on early systems, both fuel injected and carbureted, there was no computer to control the amount of fuel necessarily. There's mechanical systems for both carburetors and for early fuel injection systems. And then we had some electronic fuel injection systems that would do some basic strategy to control the amount of fuel, but not fine tuning it. And then in the mid 70s, Volvo was one of these that came out with a feedback system. We saw some other European manufacturers in the 70s. And then we saw it on domestics in the late 70s or 80s, where we were actually looking at the amount of leftover fuel in the exhaust system and then adjusting accordingly. And that's an oversimplification of what we were doing or how we were doing it, but it kind of gets you thinking in that process. I'm going to break that down a lot more specific coming up shortly. Explain the principles related to gasoline fuel systems, provide the ideal air fuel mixture for operating conditions of the engine. So my ideal mixture is going to change under conditions. Obviously, if I'm trying to climb a hill, my ideal mixture is very different than if I'm going down a hill or if I'm cruising at steady speed on the highway. As I mentioned, fuel has to be vaporized through atomization. Modern gasoline vehicles all use an EFI system, and pressure differentials central to all fuel systems. So this is where the book kind of goes off in pressure again. They did this in some other systems and they kind of get into it here. And yes, it's a pressure differential, but how they explain it is really confusing in the book. You know, if I have something that, for example, I turn on my garden hose, hopefully water comes out. Well, water comes out because of the pressure differential between the pressure on the water hose and the pressure in the atmosphere outside. Most of us say it's because the water is pressurized. That's why it's coming out. Other people say, well, no, the water is drawn out by the low pressure in the atmosphere compared to the pressure in the water system. Both are, from an engineering scientific standpoint, correct. I think one is far more confusing than the other. Being a simple guy that just fixes cars, I prefer to think of, yeah, there's pressure in the hose. That's what pushes the water out of the hose. I don't need to think about, well, yeah, well, that's because atmospheric pressure is less than the pressure in the hose, and we have this differential. I'm not trying to be an engineer, and I'm not trying to make you engineers either. So the book does get a little confusing on this. So I can think of low pressure, a vacuum can suck something. I know that because when I go get a milkshake and I have a straw, I'm able to pull the milkshake up through the straw. And again, the argument would be that the pressure in the atmosphere is pushing the milkshake through the straw into my mouth, because my mouth has a lower pressure than the atmosphere. And again, from an engineering standpoint, that's correct. From a person who just wants to enjoy a milkshake, I just want to think if I suck on the straw, I get milkshake, and I really don't care about the pressure in the atmosphere. So I think that's an easier way of understanding what's going on, especially when we look at fuel. So here's a couple of different examples. The main difference in carburation and fuel injection is the carburetor works off pressure below atmospheric pressure, vacuum, and the fuel injection system works off pressure substantially above atmospheric pressure. So what they're really saying here is we're creating a low pressure area either here or both to draw fuel out of what we call the float bowl. So this is the float bowl of the carburetor. Fuel comes in here through a valve called a needle and seat. The float controls the height of the fuel level in the float bowl. And based on the height of this level, as we have low pressure events, it allows us to siphon fuel through this system. If the float level is too low, it's going to take more vacuum to siphon the fuel. And if the float level is too high, it would take less vacuum to siphon the fuel. So a high float will cause me to run rich, low float will cause me to run lean. And we see this mostly through main metering. So I'm going to go through, not today, but I will go through the different basic parts of the carburetor, the different circuits, and exactly how we're pulling fuel through. Compared to a throttle body fuel injection, here we're controlling air. So I have more air pressure here than I have here. So the blue area is low pressure, but yet I'm spraying fuel here. Why? Because I have higher pressure in my fuel system. So when we open this up electrically, fuel is allowed to spray out into atmospheric pressure. So these throttle body systems range anywhere from a low of about 9 to 13 pounds up to a high of about, let's see, yeah, they did have some that were in the 50-pound range. Typically 30 to 40 pounds is our high pressure system for this, but they did have some stuff that was slightly higher. So subsystems of modern fuel injection systems, we have our fuel supply system, provides pressurized filtered gasoline to the fuel injectors or carburetor. Our air supply system, also called our air induction system, provides clean filter air for combustion in the engine. And 507B gets more into the air induction system. I leave that chapter for them just because of time constraints and how the classes are set up right now. Our fuel metering system constantly meters and adjusts the amount of fuel that is the engine is burning. So our fuel metering system, whether it's a feedback system or not, is we're not just pouring gasoline into the engine. We have to meter it. We have to control the amount. If I have too much fuel, I'd run too rich, get black smoke out. If I have too little fuel, my car might not run, might not be able to go up hills and so on. So gasoline fuel is derived from crude oil. Matter of fact, at one time, gasoline was a waste product. The question is, what do you do with it? It's worthless. This is back in the 1800s when most oil was refined for, number one thing was kerosene, because we used kerosene lights, and gasoline was a byproduct of that, highly flammable and unsafe to do anything with. So much of it was either dumped into pits or just burned off. In processing gasoline from crude oil, more volatile compounds raise to the top of the tower, while less volatile compounds stay low in the tower. Gasoline vapor is allowed to mix with air, and in the open is highly explosive. So in order for gasoline to be explosive, it has to have air. Vapor lock is something that we had on automobiles back in the days of carburetors. And it happened because the gasoline would actually boil in the fuel line between the gas tank and the engine. And it did that because we used a mechanical fuel pump that used vacuum to pull the fuel from the gas tank to the engine. And since as we lower pressure, we also lower the boiling point of a liquid. And so therefore gasoline on a hot day would boil and then the car would start running. That was called vapor lock. With fuel injected vehicles, we've eliminated that because now that fuel is under pressure going from the gas tank up to the engine. Therefore, we have raised the boiling point of the gasoline and it can't vaporize. So vapor lock is something of the past, very, very common 30 plus years ago when there's a lot of carbureted vehicles out there, especially on trucks and motorhomes. Gasoline is mainly a mixture of paraffins and other chemicals, along with some organic compounds and contaminants such as sulfur. So gasoline today does not have sulfur, and it's all filtered out because sulfur, some of you may remember hearing about acid rain. Sulfur was one of the main contaminants that caused acid rain. You don't hear about acid rain anymore. It's because we don't put sulfur in the gasoline. Sulfur was used as an anti-wear agent. So as they got rid of sulfur, they had to re-engineer some of the metals inside the engine to make them last longer. So here we're looking at gasoline fuel. So here we have natural gas, 68 degrees, gasoline, petrol, 300, kerosene, 390, diesel oil, 570, fuel oil, 700. And you get into lubricating oil, paraffin, wax, asphalt towards the bottom. So you put crude oil in, you cook it, and then at different temperatures, you're able to get out these different products. So you can see in the old days of making kerosene, you got all this highly flammable gasoline. I mean, factories would get burned down, people would get killed because they didn't know how to deal with this gasoline. It was a waste product that they were getting out. They really wanted the kerosene at that point. You'll hear me talk about diesel oil as diesel oil, not necessarily diesel fuel, and certainly not confused with gasoline because it is more of an oil. Fuel oil, if you ever live back east, a lot of houses heat with fuel oil. And of course, lubricating oil, we use in our engines and all kinds of other places, get grease from it, things like that. So gasoline must be enhanced with different additives such as detergents. And detergents are designed to keep the fuel system clean, help prevent knocking. They have an octane rating to the fuel. A couple different methods of measuring octane. One is the research octane number, and the other is the motor octane number. Higher octane by itself does not mean higher energy output. So in other words, just putting super in your car doesn't necessarily mean you're going to get more power. You certainly could. What it does is allows me to tune the car differently. So the higher the octane, the more energy it takes to break the bond of the hydrogen and carbon molecules. So as we increase the octane number, it takes more heat, more energy in order to ignite or burn that hydrocarbon molecule, because you have to actually break the bonds between the hydrogen and the carbon. So a low octane number would allow a vehicle to what we call pre-detonate or ping, where if I'm going up a hill or a light throttle, I might sound like a bunch of rocks in a can inside the engine. And this was very common on older vehicles. Newer vehicles use a computer and usually use a knock sensor to prevent that from happening, so you don't hear it the same way you did. Today, cars just get detuned. So if you have a car that requires 91 octane, but you're running 87 in it, going, see, my car runs fine, I'm getting away with it. Well, what's happened is the computer is detuned the car so you can get away with it. So you have this nice Mercedes, BMW, or other performance car that's requiring 91 octane, but you're running 87. So you paid a bunch of money to get a car, and then the car is not going to perform how it's designed because it's had to detune itself because of the fuel that you're using. Also, depending on manufacturer, the additive package in at the higher octane fuel, the 91, may be far superior to the additive package you may get in the other things. So there are some additive differences, again, depending on gasoline manufacturer. So, the octane rating directly relates to what temperature the fuel will ignite at. So I can advance my ignition timing, which gives me more performance, more power, much farther with a higher octane fuel than I can a lower octane fuel. So I can, again, so that comes into our tuning. I can do a lot of stuff with better fuel. And so fuel is a key thing. On the other hand, if you have a car that's designed for 87, you're really not getting a benefit out of putting 91 in it, other than the additive package. So for example, Chevron uses a completely different additive package in their super or in their premium than they do in their low grade and mid grade. It's a different additive package. So you're not only getting the octane, you're getting better additives. So there can be reasons for that, depending on how long the car sits, how you drive, and so on. If the octane rating is higher, what effect will this have on the temperature the fuel ignites?
Number
Number
3.
one. Number one.
No,
Number one,
number 1.
you'll ignite at a higher temperature. So conversely, low octane fuel ignites at a lower temperature. That's why it ignites before we want it to, hence pre-ignition. Engines perform best when used with the octane recommended by the engine manufacturer. Octane can be boosted with additives. One of the most common additives we use is alcohol, which has its own downsides. Octane is now boosted with additives of ethanol, aromatic hydrocarbons, other chemicals. So there's a couple of different ways to get octane out of fuel. One is you can refine it better, but it's cheaper just to add alcohol. So it helps keep the cost of fuel down. Also, alcohol is beneficial for emissions, but you get less gas mileage. So alcohol burns cleaner, but you don't get as much power out of it. So gasoline that you're buying today at a pump in California is going to be gasohol. You're not really buying gasoline. It's a mixture of gasoline and alcohol. It's normally ethanol, and most in cars can normally run up to 20% alcohol without a problem today. Most cars are rated at up to 20%. The alcohol content we have in fuel here in California is 10% across, doesn't matter what grade you buy. So you have a 90-10, and this would be designated as an E10 mixture. If you have a flex fuel vehicle, have a yellow cap on your gas tank, it'll tell you that you're able to run E85, which would be an 85% alcohol to only 15% gasoline. Now you get a lot fewer miles to the gallon because you have less energy in the alcohol than you do in the gasoline. And then we can get into how much energy is used to produce the alcohol, and you're losing. So it's one of those. So the alcohol allows them to move the octane up higher with less refining. But when we look at it from an emission standpoint, I'm sure it's improved, but back 20 years ago, when it was really, really big and it was a new thing, it took a gallon of gasoline to produce a gallon of alcohol, and a gallon of alcohol doesn't go as far as a gallon of gasoline. So it was a negative thing as far as transportation, but it was very popular because it was seen as green, it was seen as renewable, even though you get a net loss of fuel producing it. So we still see that today. Oil companies are currently still lobbying to be able to keep alcohol in their fuel, largely because of cost. It's the cheapest way to get the octane. There was just some hearings on it in Congress earlier this year or late last year. They all blend together. I was watching. So gasohol, commonly used as alternative fuel in motor vehicles. Fuel system and engine modifications are normally not needed for 20% alcohol or less, or E20 or less. Many gas stations sell gasohol as high octane fuel. 10% alcohol can increase 87 octane to 91. This is California gasoline. This is also why our gasoline goes bad so quickly, because gasoline itself can stay stable for years. Alcohol is stable for about 3 months. So this is why, a lot of times people have problems with their lawnmower or their lawn care equipment or cars that sit. It's because of the alcohol in the fuel. That's where the problem is. A gasoline mixture with 15% alcohol will be marked with which of the following labels?
Number 2.
Not number 2.
Mm.
It has 15% alcohol. So which were these labels would I expect to see?
Is it number 4?
Okay, number 4. So E85, that would be 85% alcohol. So the E stands for ethanol. And the number
Oh,
after
okay.
it is the percentage of ethanol.
So it's number 3.
Number 3. I knew you guys had the right answer. So it's easy to remember. You just remember that the E stands for ethanol, and then it's the percentage of ethanol. On diesel vehicles, you'll see a B, and then a number after it. The B stands for biodiesel, and then it'd be the percentage of biodiesel in the fuel. So if you have a vehicle that you put diesel in and you see a square tag and says B and a number after it, that means that the fuel you're getting is that percentage of biodiesel. So controlling fuel burn. So we're going to talk a little bit about stoichiometry before we get into the physical part of this, because we're going to talk about our different systems and we're going to talk about trying to control how long we turn them on for. And I think it's important for us to look at what the goal is. Where are we trying to get to? So this, I could put this in the fuel control section, and it still is there, but it kind of has it in the book here, and I kind of gone back and forth. So right now I really have it here. So a lean air mixture has more air in proportion to the amount of fuel. A slightly lean mixture gives good fuel economy with potentially low emissions. A rich mixture has less air in proportion to fuel. So what we're looking at here is the air fuel ratio for gasoline. Now keep in mind, we don't run gasoline in California, we run gasohol. But the air fuel ratio, where all the fuel and all the oxygen is burned, is about 14.7 to 1 by mass. By mass, they mean weight. So it's 14.7 pounds of air for every pound of fuel. So if I want to do that by volume, space, I would need about 11,000 of these cups with Tigger in it of air for every 1 cup of fuel. That's volume. What we deal with is weight. And it's real important because a lot of times you'll see this written as parts. 14.7 parts of air to 1 part of fuel. Well, parts, I cook a lot, right? 2 parts, that's 2 of these to 1 of these, right? That's parts. That's cooking. You're mixing. Parts is volume normally, not weight. And I've actually, one of the things I get to do is I get to sit on an evaluation committee for instructors that want to be licensed in the state of California to teach the emission program. And I have failed a lot of instructors because they get that wrong. So these are instructors that are teaching students and they flat out get it wrong. And the reason why it's so important is that everything we do with our computer in measuring fuel is all about weight. We know exactly how much the fuel weighs on a modern fuel injected vehicle. What we don't know is the weight of the air coming in. That's why we have all these sensors. We have our mass airflow sensor or MAP sensor. We have our intake air temperature sensor, our engine coolant temperature sensor. We have all these sensors because we're trying to measure the weight of the air. Once we know the weight of the air, now I can try to put in the correct amount of fuel. And so that is what we spend our time doing. Our computers, going way back from since we first started trying to balance this, we're all about weight. And so if we're going to diagnose these cars, it doesn't make sense to understand its weight. So this is in your book, and this is really bad. This diagram, it's horrible. It is way out of calibration. So it says here your normal operating range of lambda is 0.9 to 1.1. That is a lie. That is not the normal operating range of lambda. The normal operating range of lambda is much, much smaller than that. It is actually 0.980 to 1.020. So you can see a fraction of what the book is showing here. So a slightly rich mixture, less than 1 lambda. We see we have high CO emissions. Fuel consumption is going to be not as good. I want to use more fuel, but I get more power. As we go lean, power drops off, fuel consumption gets better, and carbon monoxide emissions drop. Now, like I said, this chart is, aside from being way out of scale on where the lines go, because it's actually much, much more sensitive than this as far as how the emissions work compared to the mixture. The mixture range is way too big. So we can talk about 14.7 to 1, and that is a need to know. Okay, it's an auto class, you need to know that. However, for alcohol, the stoichiometric ratio, or the ideal ratio, is 9 to 1 for ethanol. Well, that's not 14.7. So if I mix alcohol with gasoline, I probably don't want to be at 14.7 anymore. Otherwise, I'd be too lean. I got 10% alcohol. So I could try to figure out what that new number is based on how much gas is in there, and remake the chart, and can get really confusing. Or we can use this other thing called lambda that I will get into shortly. And a lambda is the ratio of oxygen available to oxygen required for complete combustion. In other words, what's the ratio of oxygen atoms to carbon atoms, and did we use everybody? If I have more oxygen than I need, my ratio would be over 1, or over 1 lambda. If I have less oxygen than I need, my ratio would be less than 1 lambda. So this is a formula, and I'll get to it coming up. But the thing is that lambda automatically adjusts for the type of hydrocarbon we're using. So a lambda value of 1 for gasoline is 14.7. But a lambda value of 1 for alcohol is 9 to 1. So it automatically compensates for our fuel mixture that we're using, which is really cool. So when we look at diagnosis on cars today, we look at what's going on. It's all about lambda. We don't use air fuel mixtures. We don't say, gee, 15 to 1 is lean. And you need to remember that. And 14.5, well, gee, that'd be rich. It's all about lambda today. So we're going to get in and look at lambda. But a slightly rich mixture can produce more power, but use your extra fuel, steps up fuel consumption, and greatly increases emissions, some emissions. However, extremely rich mixtures can foul spark plugs, increase carbon deposits in the combustion chamber and exhaust. So we have some real issues with going too rich. So if I want to race a car, I'm going to go rich. I get more power, right? So especially if I'm only going a quarter of a mile. I don't need to worry about carrying enough fuel with me. I can go a quarter of a mile. If I'm going on a round track for 500 miles, now I might not want to run quite as rich, because now fuel consumption becomes an issue. So combustion, flame spreads faster and moves evenly to halfway through the mixture. Combustion ends with the piston a short way down the cylinder. So it bottom dead center, and of course it'd be nice if my piston was actually moving more here. The spark plug fires before top dead center, and the mixture ignites. So a certain number of degrees on most engines, there's a couple exceptions, before my piston comes all the way to top dead center, we're going to start burning the fuel. We're going to ignite it with the spark plug. At top dead center, the flame front expands, cylinder pressure starts to rise, the piston is going to start coming down, and partway down, it's going to reach the maximum pressure in that cylinder, where it's going to really push that piston down. And we don't want to be doing that straight up and down, because our connecting rod and our journal are straight up and down. I need to do it when we're bent a little bit, so I've got leverage when we hit that maximum pressure. So at some point after top dead center, all the fuel is ignited, and we get our maximum cylinder pressure to push the piston down and accelerate the crankshaft's rotational speed. What is the stoichiometric fuel mixture for gasoline?
Number 4.
Number 4.
Number 4, you got it. So detonation and pre-ignition, these both sound the same to the driver, but they happen for 2 very different reasons. Detonation is a violent collision of flame fronts in the cylinder caused by uncontrolled combustion. So in this case, what's happened is we have two sources of ignition. The source of ignition from the spark plug, along with the source of ignition normally from a carbon deposit or a hot spot. And so pre-ignition occurs before normal ignition happens, hence the term pre-ignition. So we fired off, my fuel has exploded basically before the spark got there from the spark plug. So octane, the incorrect octane level causes pre-ignition, big cause of it, because it is too volatile of a fuel and the engine is designed for a more stable fuel. Detonation occurs after normal ignition, normally from a hot piece of carbon. Also can be caused by incorrect fuel. Can cause severe damage unless we avoid it. So you can put a hole through a piston in less than 1,000 miles with either of these. So this is something that you cannot allow to continue. That's why, on modern vehicles, the computer prevents this from happening. Many engine management systems use knock sensors to detect detonation or pre-ignition. An engine that keeps running after it's switched off is said to be running on or dieseling. So another thing we have is, and we saw this on older carbureted vehicles, we don't see it on fuel injected vehicles now unless they're extremely overheated. But you turn the car off and it comes and then finally stops running. So very, very common on carbureted vehicles. The only two things that can cause that is either an engine that's idling too high or a mixture that's too rich. So if I have a carbureted vehicle and I shut it off and it doesn't just shut off real nice like a fuel injected vehicle was, and it and then finally stops, one of two things is happening. I'm either running too rich, excuse me, or I'm idling too high. So in other words, I can run a really rich mixture if I bring the idle speed down, or I can run a higher idle speed if I lean out the mixture. One of the old urban legends is that ignition timing causes dieseling or run-on. That's false. It does not cause that. Now, sometimes as you adjust ignition timing, you may lower the engine speed if you don't readjust it. And therefore, gee, it doesn't diesel anymore. Well, it doesn't diesel anymore because you lowered the engine speed, not because you adjusted the timing. So timing cannot cause that. And that little bit has made me a lot of money over the years fixing these vehicles. Also kept me from getting distracted by technicians that thought that timing caused that. And I learned very early on, I was taught well, that it's either idling too high or running too rich. Those are the only two things that will cause it. Leave the timing alone. Timing, ignition timing can cause some detonation problems, but it's not going to cause dieseling. So detonation and pre-ignition. Here the book shows a hot spot in the cylinder, ignites the mixture before the spark plug. Here the hot spot ignites it after the spark plug. Both of these will cause excessive emissions. It'll cause you to have unburned fuel because these two flame fronts collide. Hydrocarbons in the middle and oxygen in the middle are not going to be used. So you're going to have unburned fuel coming out the tailpipe. You're going to have what's called oxides of nitrogen emissions, which is where the heat, we have a superheating event over 2,500 degrees in the combustion chamber. And we actually bond the oxygen and nitrogen molecules in the atmosphere we're breathing together to form oxides of nitrogen, or NOx as it's commonly called, which is one of the major components of photochemical smog. Not to mention, this is extremely harmful for the engine. What will happen is it'll actually eat away at the top of the piston. And once it gets down to this top land where you're exposing this ring, the engine's done. I've actually seen it where it puts holes all the way through the piston or burns out big sections of the piston. So this is something, especially you have to be careful of it on trucks where you're going to do any towing or hauling or heavy load, is where we see this really catastrophic on engines, because you're putting much more strain on what's happening, and you're more likely to you're going to generate more heat while you're towing, which is going to exacerbate a already pre-existing condition that would cause detonation or pre-ignition. Dieseling can be caused by high idle speed, an overheated engine, too many carbon deposits in the chamber, or gasoline with octane rating is too low. So this is right out of the book. So, and they're right. So a high idling speed is not going to cause detonation or pre-ignition. High idling speed will cause dieseling, but it won't cause you to ignite or have carbon in there. It's going to ignite the fuel mixture. An overheated engine, yes, absolutely, because that's excessive heat. If I have the heat, that's what ignites the fuel. Too many carbon deposits in the chamber. You don't have to have too many carbon deposits. You just have to have carbon deposits that are getting really hot. It only takes one. Or use of gasoline with an octane rating is too low. That's correct. But where the book says high idle speed, it's not going to cause detonation or pre-ignition. However, dieseling, I'm sorry, I misread this. Dieseling can be caused by high idle speed, an overheated engine. Carbon deposits are not going to cause dieseling. Octane rating is not going to cause dieseling. Now, I can hide a dieseling problem. In other words, I can hide a mixture by running better fuel. But the fuel itself is not causing it. A solenoid can be used to close the throttle to below idle position. So we had what's called a fuel cutoff solenoid on carburetors to keep them from doing this. Fuel injected vehicles do not experience this unless you have a leaking injector, which I've never had, or it's extremely overheated. The only time I've ever seen a fuel injected vehicle diesel is when it's been just extremely overheated, like 260 degrees overheated. So air, one of the essential components, the internal combustion engine. So air is fuel, specifically oxygen. So we are, roughly 80% nitrogen and 20% oxygen in round numbers. You can see here, we've drilled it down a little bit better. Oxygen is highly reactive and promotes combustion. So we call combustion oxidation because we're actually combining the oxygen molecule with the carbon molecule. Argon, carbon dioxide are trace elements in the air. So when we talk about carbon dioxide, you see up here it's a percentage. It is currently just over 400 parts per million is what we have for carbon dioxide in the atmosphere. Very, very low number. So if we look at our fuel, we're combining air with fuel, and we're doing that in order to oxidize our hydrocarbon fuel, combustion. And if I look at the emissions coming out the tailpipe, so if I combine oxygen and hydrogen, I get water. That's a good thing. We like water. And matter of fact, for every gallon of gas your engine burns, it produces about a gallon of water. Hydrocarbons are unburned fuel. This is fuel that went through the engine and was never oxidized. Carbon dioxide is combining the carbon with oxygen, CO2. We want that. So the gases we really want to have come out of the tailpipe are H2O and CO2. In a perfect world, that's what my car would put out the tailpipe. CO2 and water. That's it. If it was a perfect world. Oh, and nitrogen, obviously, which I don't have here because we have so much nitrogen going in. Nitrogen is going to come out the tailpipe. But as far as reactive gases, I really only want water and carbon dioxide. Carbon monoxide, CO, is a pollutant. So again, we're combining carbon with oxygen, but I have a lack of oxygen, so I can't make carbon dioxide. So carbon monoxide, which is poisonous and also a pollutant. So that's a bad thing. Oxygen, if I have oxygen coming out the tailpipe, that means I didn't use it to oxidize my hydrocarbon, means I'm running lean. I had too much oxygen. So even though we have oxygen in the atmosphere, I really don't want oxygen coming out the tailpipe. I want to be using all the oxygen. I don't want to be putting in the right amount. And then NOx, which I mentioned earlier, oxides and nitrogen, is combining the oxygen and nitrogen in the atmosphere, where we have something under pressure over 2,500 degrees Fahrenheit. We now bond those two molecules together. And NOx is a major element of photochemical smog. That's the smog we have in the LA basin, or we might have an El Cajon, or we have those, we don't have smoggy days like we used to. We used to really have smoggy days. So stoichiometric ratio. So stoichiometric balance describes the chemically correct air-fuel ratio necessary to achieve complete combustion of the air fuel that's been introduced into the engine. For gasoline fuel, stoichiometric air-fuel ratio is 14.7 parts air to 1 part fuel by mass, weight. Now, why they just couldn't have said pounds here and made it less confusing is beyond me. Pounds, kilograms, whatever, I don't care what system we use. A mixture with a lower lambda value has proportionally less air than fuel. The exhaust oxygen sensor is used to indicate the amount of oxygen in the exhaust. And actually, that's not true. That's not what oxygen sensors do. It's an oversimplification. And B, oxygen sensors, believe it or not, don't measure oxygen. They actually measure lambda. They're a lambda sensor. Because if I put an oxygen sensor out here in the atmosphere, it doesn't measure anything. And there's tons of oxygen out here. So they're far more complicated than that. So the book really overly simplified it here. So we really use the oxygen sensor, and they weren't originally called oxygen sensors. They were originally called lambda sensors. It wasn't until Ford and Chevy got a hold of them and realized Bubba didn't know what lambda was that we had to call it something he could relate to. So we called them oxygen sensors for years. And that was good enough to fix most cars for a long time until we got into the 2000s. And then that definition really didn't allow us to fix cars properly. And we had to drill further and see exactly what is it doing and how does it work, because we've evolved in how we're using it. So the density of the air is its mass per unit volume. A volume of air at a high density has a higher mass than the same volume at low density. So all they're saying here is that the air at sea level is heavier than the air in Denver. The density of the air also changes with what? Temperature. So on a cold day, the air is heavier than it is on a hot day. That's why, like drag racing, they really like 50-something degree days because the air is heavier. You're going to get better race times. On a 90-degree day, you're not going to break any records. The air is too thin. You're not going to get enough power out of the engine. So there's a direct correlation of the air's weight to both altitude, which is pressure, and temperature. So let's take a look at what lambda is. So lambda is oxygen balance. So lambda, we got a little lambda symbol here, equals oxygen available to the combustible's demand for oxygen. In other words, oxygen required. So if my ratio of oxygen available to the amount of oxygen I need is the same, I would have a lambda value of 1, and that would be 1.0 to infinity. So anything above or below 1 is either rich or lean. So as soon as I go 1.0001, that's a mixture that is leaner than stoichiometric. If I have a mixture that's 0.999999 forever, that's a mixture that's richer than stoichiometric. Now, both of those would be acceptably lean and acceptably rich, because we don't just keep our mixture at one point. We constantly move it rich, lean, rich, lean. We're constantly moving it above and below 1 lambda. And we have to in order for the catalytic converter to work. So a modern vehicle is constantly going rich, lean, rich, lean, rich, lean. We're not staying at one point. We want to have an average at one point. So that's critical. So lambda is the ratio of O2 available combustion process versus the combustible's demand for O2 to attain complete oxidation. In other words, everybody has a partner. We went to a dance and everyone's partnered up. There's no one sitting on the chairs, sitting out the song. Everything is here. So that is what we're really trying to do. We're trying to match up, does all of our hydrogen atoms and carbon atoms, were they all used? Did they all match up correctly? And so that's why we use a lambda sensor to measure this. Lambda is equal to 1 when the O2 and combustible demand for O2 are in balance, perfect stoichiometric point. So lambda control is necessary for peak combustion efficiency on the engine. Lambda control is necessary for peak catalytic converter efficiency. Our catalytic converter will not function correctly without good fuel control. Lambda control improves reliability, fuel economy, lowers emissions, also increases engine life by better managing our fuel control mixture. So engine out combustion efficiency for gasoline fuel is no better than 95%, typically down around 90%, but we've made it a little better. So this is, when I talk about combustion efficiency, we're not talking about heat power. We're not even talking about power coming out of the fuel we're burning that we're able to use to go down the road, because we know some of that's used through our cooling system, some goes out the exhaust, some is parasitic loss, and so on. But we're really talking about the efficiency of the burn. How much did we oxidize all of the available hydrocarbon? And currently we're at about 95%. So that is why we use a catalytic converter, is to get that 95% and take it up to closer to 100%. Sometimes we do hit 100%. And here we're looking at 99 to 99.5. But basically the catalytic converter gives us a factor of 10 improvement. So the catalytic converter is not designed to make a dirty car run clean. It's designed to make a clean car run cleaner. And this is required for current emission standards. And the catalytic converter, or CAT as we call it, combustion efficiency is very lambda dependent. So we combust in two different areas, or we oxidize our air fuel mixture in two different areas. One's in the combustion chamber, the other's in the catalytic converter. Those are the two places that we oxidize fuel. That's where we burn the fuel. We burn it in the engine and we burn it in the catalytic converter, so that when it leaves the catalytic converter, all the fuel has been oxidized. If we haven't oxidized everything, we're polluting. So a balanced equation that calculates lambda. So some people go, okay, great. Well, here's the math formula. And I did do this in a class a couple of times ago, and I had someone go, oh, I can do that. Good for them. I can't, and I'm okay with that. That's why we have calculators, right? So just like with this, I could do this longhand and spend a lot of time, and I'd probably never use it, make my head hurt really bad. Or I can put the numbers I need into a calculator that I'm going to show you, and it'll give us a lambda calculation. But this shows you that this is a very involved calculation. So this is not a simple, you know, gee, I'm just guessing, right? This is not a, gee, I think it's about this ratio. The magic of this formula is it accounts for all of our hydrocarbons and all of our oxygen, and then is able to come up with the number. It's able to balance it. So it's kind of like taking a deck of cards and throwing them on the ground. And then I'm going to use my formula to figure out, do I have 52 cards? Do I have 4 kings? Are the kings each of its different suit? Are these the 4 suits I'm supposed to have? And we do this by measuring the tailpipe emissions. So by looking at what comes out the end, coming out the tailpipe, I can determine what went in the front. And so this allows me to see this regardless of how well the catalytic converter is working, regardless of how well the engine's running, all those things. I'm able to see through all of that and figure out what went in the engine. So this is a huge tool, kind of almost like X-ray vision. So a lambda of 1 is when the oxygen available and combustible demands for oxygen are in balance. And this is the point of perfect stoichiometric balance. Stoichiometrics, sorry. At this point, the AF ratio is 14.7 to 1 for gasoline. Keep in mind, we don't run gasoline. So I really don't care what my air fuel ratio is. I care about my lambda if I'm going to diagnose a car. So thus air fuel ratio equals 14.71 times whatever my lambda is. So if I want to figure out what the air fuel ratio is, I could take lambda times 14.7 to 1 and come up with an air fuel ratio. Now that only works if what? I'm running purely gasoline. Sensitivity to combustion efficiency, pre-cat versus post-cat, or pre-catalytic converter versus post-catalytic converter. Lambda uses all the oxygen bearing and combustible bearing gases. Therefore, it's not affected by the degree of oxidation. So if I have a weak cylinder, bad spark plug, bad catalytic converter, no effect. This method is insensitive to combustion efficiency. So either pre-cat or post-cat gases can be used. Lambda equals 1 when the oxygen available and combustible demands are in balance. The ECM controls lambda equals 1 at 0.5 to 1 cycles a second using the lambda sensor input. So first of all, not all manufacturers run their vehicles at 1. It's close to 1, but many times it's not 1. It might be 0.999, might be 0.998, might be 1.001 or 1.002. It may be as rich as 0.94 to 0.98 or 0.940 to 0.980 in the case of BMW. You will have different ranges that manufacturers do. They don't all run at 1 lambda, and they do this for different reasons. And that's because as we go lean, certain emissions increase, and as we go rich, certain emission increases. So based on what we want for performance out of the vehicle, what other emission control devices are placed on the vehicle is going to determine where that manufacturer decides to run their fuel mixture. Three-way catalytic converter operation, which is what we use on all cars today, requires lambda to be between 0.980 and 1.020. If it is not in that range, the catalytic converter will not work. And even within that range, the catalytic converter does not work equally throughout the range. So if I have a car, for example, that's failing smog, the first thing I do is check the lambda, because if the lambda is out, I got to fix that first. If the lambda's in, now I can test things like the catalytic converter. So I can't even test a catalytic converter or think about replacing a catalytic converter if a car's not in fuel control, because it won't work. It'd be like replacing a computer because the computer doesn't turn on without checking to see if the outlet has any power in it first. So lambda can be confirmed by the exhaust reading is measured either pre or post cat. So a lambda value of 1 represents what air fuel mixture for gasoline?
Number 4.
Number 4. So in order to calculate lambda, I'm going to use a lambda calculator. The one I use happens to be on IATN, which stands for International Automotive Technician Network, and is available to IATN members online. This is a free membership. It's a plug and play with either 4 or 5 gas values. Can select either US or European gasoline. It says it runs in Java, can be saved and run offline by Java Quick Router. I've never been able to do that. So here's our lambda calculator. So what I'm going to do is I'm going to take the gas readings from the tailpipe, in this case off of a failed smog report, but I could do this off a live test or whatever. I'm going to put these numbers in. So 14.6% CO2, 0.05% CO, 10 parts per million of hydrocarbons, no oxygen, 908 parts per million of NOx, and I click calculate. And since I used 5 gases, I'm going to look at the 5 gas measurement. It tells me my lambda value is 1. So although this car failed for high NOx, what the test did is it proved that it's not a mixture problem. So now I had to go in and diagnose the emission control systems that are designed to help control NOx. And I found a split vacuum line going to an EGR valve. But the point is that my lambda proved what's not wrong very quickly. Here's another example. In this case, 13.8 CO2, 0.78 CO, which is carbon monoxide. Hydrocarbons, 123 parts per million. 0.7% oxygen and 1,940 parts per million NOx. So this car again failed badly. But when I run the Lambda, I can see I'm in fuel control. I'm less than 1.020. I'm at 1.008, so not perfect, but I am within fuel control. Now, keep in mind, both my engine and my catalytic converter are supposed to combine oxygen with hydrocarbons to make CO2 and H2O that we're not measuring here. So I'm not making as much CO2 as I want, and yet I have oxygen here, I have CO here, and I have HC here, but my catalytic converter is not putting them together. In this case, this car had a couple problems, but one of which was a bad catalytic converter. So you can see where very quickly I'm able to leverage this information and see what's going on. So this is how we control fuel. So here's another vehicle. And this one here, CO2 is at 15%, which is about perfect. We normally want to see about 14.7 to 15. No CO, no HC, 0.4 oxygen, and 2,334 parts per million of NOx. And my lambda value is 1.023, which is outside of my range. It's at 1.020 is my max. So I can't even test the catalytic converter. And this car happened to have high mileage, didn't have a lot of emission controls on it, and was looked at as, I think most shops would have just put a catalytic converter on this, but by using Lambda, we were able to go through and see, and what we found is it had a bad oxygen sensor. And when we fixed it, it went down to nothing. I think I went down to 4 parts per million or 2 parts per million. I mean, it just went down to nothing. But this allows us, so what Lambda does is it gives us discipline. This is what the computer uses to control fuel. And this is something we can measure when we're doing diagnostics. Here's another example here, 14.6% CO2, 0.02% CO, 15 parts per million, 0.4 oxygen, 1,497 parts per million of NOx. When we put in the Lambda calculator, we find out that we're at 1.021. It's out of fuel control. So even though this is an older vehicle, you could guess and go a lot of directions. What this tells us is that it's a fuel control problem. We have to fix this first. And what we found was a misrouted vacuum line. Someone plugged it into the wrong port, causing the high tailpipe emissions. And we moved the vacuum line, and not only did the car pass smog, it continued to pass smog the next 3 times it was tested, or so next 6 years. So total of what? Yeah, 6 years. And this was on a older car, 1980s car, 89 Saab actually. So you can see where it still had the original catalytic converter, still had a lot of original stuff on it, but you can see here where this really prevents people from jumping to the conclusion of, oh, it barely failed, it probably needs a catalytic converter, or it probably needs this, it probably needs that. You know what, if you have a car that still gets a tailpipe test for a smog inspection, before anything happens, you should be running a Lambda calculation to see where it's at. If it's not in fuel control, we need to fix fuel control, which we're going to talk about in this module. If it's in fuel control, then we need to look at emission controls, which we'll look at the emission control module. Here's a vehicle that's running rich. So this happens to be a truck. And I've got CO2, 14.3, 1.16% CO, 242 parts per million, 0.3% oxygen. We did not measure NOx, because in order to measure NOx, I have to drive the car on the dynamometer, and this truck was too heavy for the dynamometer, so it did not get that type of test. So this happened to be a 1-ton truck with about 165,000 miles on it. And the first thing we fixed was the fuel control, because we're running very rich, we're less than 0.980. And we found a bad oxygen sensor, and once we did that, we found a bad spark plug wire and a cracked distributor cap. So this thing passed with very low numbers when we were done. We're still with the factory catalytic converter at 165,000 miles. So, you know, catalytic converters are replaced a lot. They're replaced a lot when they don't need to be replaced. And that's an issue because they're expensive. So air fuel ratio from Lambda. So if we look here, 14.42 to 1. I get that by 14.7 to 1 times 0.98 Lambda. So that's our range, 14.42 up to 15.01. 14.71 times 1.02, we get to 15.01. So you can see the range the book gives you is way, 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 way too big. It really has to be focused in to this very tight range of where vehicles actually operate at. So that's why that graph earlier, I said it's just way, way out. It is not accurate. So the advantage of Lambda is it's accurate, uses 5 gases. Okay, so I have a question here. So what if the car years after 2000, no tailpipe emissions, would you still recommend doing tailpipe emissions to determine Lambda process troubleshooting? Possibly, yes. So I can do that a couple different ways. I can use a gas analyzer and do the Lambda calculation, which is definitely can be very useful. The other thing I can remember is that my car has a Lambda sensor, and that's the rear oxygen sensor. So I can use my rear sensor to help figure out, is the car running rich or lean, or is it running at the correct place? So I can also use that rear sensor to help determine that. Because once I understand that that rear oxygen sensor is a Lambda sensor, I can use that rear sensor for a lot of this diagnostics without having to necessarily pull a gas reading, because the type of problems I'm going to be solving on a 2000 and newer, I'm going to be able to do it by using that rear Lambda sensor, still applying what I know here, but I'm going to be chasing different problems. But yes, there is times, especially if I have a car that's running poorly and I don't have codes, absolutely, I'll still use a gas analyzer. Maybe I have a car that's running poorly and I do have codes. It says I'm misfiring on cylinder number 5. Well, cylinder number 5, I can't get to the injector or connector. I can't get to the coil. I can't get to anything on cylinder number 5 without taking the engine apart enough to where I can't run. Well, let me go throw it in the tailpipe analyzer. Because if I have a fuel injector that's not putting in fuel, I'm going to be really lean. But if I have a spark plug or ignition system or compression problem, Lambda is still going to be really close. So I can, again, I can use that to compensate. So I can look at my sensors as my first, but I can certainly use a gas analyzer as my second. Good question. Matter of fact, I'm doing a webinar Wednesday and Thursday night this week on 5 gas analysis. And a lot of what I talk about deals with Lambda. Last time I did it, what I have like 140 something people that signed up from it from the US. And actually, I guess it was all I had people outside the US also. And I saw some of the feedback as they're promoting. Some people said, yeah, I paid for it last time. I'm taking it again. It's good information. Where other people are going, you know, we don't even use gas analyzers anymore because it's old. And the guy who took it says like, no, there's good information there. And I'm spending the money to take it again. So, you know, this is still real relevant even on newer cars because it really helps us understand all the pieces of what's happening. So a lean mixture can be represented by what Lambda number? Are you?
1.
Which number?
Number 1.
It's number 2.
You're right, be number 2, because right. So Lambda is the ratio. And I see it's blurring me now. It lost me here. There we go. It's the ratio of oxygen available, sorry, Kat, to oxygen required. So that ratio is really what we're looking for. So if my ratio is imbalanced, it'd be 1.000. If I have less oxygen, my ratio would be less than 1. And if I have more oxygen, my ratio is more than 1. In this case, a lean mixture, more oxygen than I have fuel, is going to give me that ratio of over 1. So answer number 2, 1.02 lambda is lean. So lambda can fool the untrained, just like with any test we do. We need to make sure we look at the vehicle and put our results into perspective. So lambda might not be accurate if I have air injection. So an air injection system that works all the time. So we're talking pre-OBD2 vehicles here. Or an exhaust leak, both of which will cause lambda to show an artificially lean mixture. So lambda can only be used to verify fuel trim operation when there's no exhaust leak. So even on a modern vehicle like a 2000 and newer, back to your question, Bronco, I can use lambda to verify my O2 sensors are in calibration. So if I think I have something off, or I don't trust them, or I think I have bad sensors on a car, I can actually use a tailpipe test, do the lambda, compare that to with what the O2 sensors are reading to see if I have a sensor this bad. And I've done that quite a bit on cars newer than 2000. So here's an example of a calculation on a car that failed with a slightly lean mixture. So in this case, we would diagnose this as a emissions failure, even though my fuel system really isn't working perfectly. But because we're methodical in how we do it, and based on the flow charts and the book that I wrote, we're still going to trip over the problem. So at the end of the day, we're going to be fixing fuel control anyways. So it's all about that process. And it's about being disciplined. It's about not being, people all the time say, well, I think it's this, or I think it might be this. Well, I think I might win the lottery, but, it hasn't worked so far. So it's really about discipline. It's about making tests and making decisions based on the results of those tests and being very methodical. And that's how we fix cars today. We don't fix cars like we used to. You'd hear a car coming in and go, oh, I think it's this, or gee, it sounds like it's this. We don't do as much of that today. Today, it's more about testing and discipline and eliminating things that aren't wrong. What is the air-fuel ratio measured in when discussing the engine?
Pounds.
Pounds, number 2. Yep. Weight. Not volume, not pressure, weight. So pressure. So we have a chart here, and it shows 2 different pressures. One is gauge pressure, the other is absolute pressure. And we've talked about this before. So absolute pressure goes from 0 all the way up. Gauge pressure is at 0 at the pressure we're at in our room. Anything less than that pressure is vacuum. Anything more than that pressure is pressure. So my gauge pressure is here, and I can go down to 30 inches of vacuum. So manifold vacuum used to operate the power brake booster. Atmospheric pressure reduces with altitude. A pressure gauge indicates only pressure above or below atmospheric pressure, where absolute pressure equals gauge pressure plus atmospheric pressure. Readings on your tire gauge are based on gauge pressure. So when we look at engine management systems, we got to be real careful. Many of the sensors on the car, including fuel pressure sensors, measure an absolute pressure. But yet when I hook my test equipment up, I'm measuring in gauge pressure. 2 different scales. So atmosphere is 14.7 PSI, one of those magic numbers in automotive. So if I don't know whether my sensor is measuring gauge pressure or atmospheric pressure, check the reading key on engine off with the pressure sensor removed from whatever the pressure source is. So if it's a fuel pressure sensor, I need to bleed the fuel system down so there's no pressure in it. But yet if I bleed it down and there's no pressure in it, I have no fuel pressure and it's still reading 15 pounds, guess what? It's reading absolute pressure. If it reads 0 pounds, it's reading gauge pressure. So that's something that sometimes the repair information will tell you. Many times it will not. So be real careful of that when you're looking at data on a scan tool as to what it reads. So pressure below atmospheric pressure is called vacuum. A vacuum gauge is normally used to measure it. Most gasoline engines, the position of the throttle plate controls the volume of air or air fuel mixture entering the manifold. So the position of the throttle plate hasn't directly controlled the fuel going in the engine since the carburetor. All it controls is the air. Now, the angle of the throttle, which the computer measures, will determine how much fuel the computer wants to put in the engine. In other words, if I put my foot to the floor, the computer knows I want to go fast, it's going to put in more fuel. But the position of the throttle itself is not bringing more fuel in the way it would on a carbureted engine. At idle speed, the pistons draw air away from the manifold at a faster rate than it can pass through the throttle plate. Therefore, we have high vacuum at idle. At wide open throttle, the vacuum is much less because the throttle is less of a restriction. And we learned this in the mechanical section. So here we're looking at pressure, and here's just vacuum at idle. Here's vacuum at park throttles. We've already done vacuum testing. So a vacuum gauge can be calibrated in inches of mercury in a scale reading from 0 to 30. Some management systems use barometric pressure sensor. I can also measure it in bar, kilopascal, millibar. There's several different ways I can measure pressure. Here they're talking about atmospheric pressure. So vacuum is the amount of vacuum it takes to pull this up 30 inches. So we have inches of mercury. We have inches of water. Inches of water is more sensitive because water weighs less than mercury. So inches of water, I have a lot more inches of water than I'd have inches of mercury with the same amount of vacuum. So now we're going to look at our actual fuel delivery components. Now that we know what we're trying to do, we're trying to manage our fuel. We're trying to keep it close to stoichiometric. And you can see how when lambda is moved, emissions go very high. Cars run very dirty. So we're going to look at several components of our fuel supply system. So fuel tank, fuel neck, gas cap, fuel pump, relay fuel pump, fuel tank sending unit, fuel filter, fuel lines, fuel rail, fuel pressure regulator, and fuel injectors. So fuel tanks have changed over the years. They used to be vented. Now you can see they have a pressure vacuum cap. We started doing that around 1970, 71 on light duty vehicles. This is a primary reservoir for our onboard fuel supply. Typical fuel tank, a modern vehicle, consists of the gas cap, filler neck, fuel pump, fuel level gauge, sending unit, and the fuel. So we've got some baffles built into this pump. Many of them today, the fuel level gauge is built in with the fuel pump assembly, and it's all one piece, and all the lines go into the top of that one piece. You can see here we have fuel out, pressure out. That fuel goes to our fuel rail. Fuel back and forth to and from the charcoal canister. This is only for vapors, so that's why we have a liquid vapor separator. We'll look at fuel evaporation systems more when we get into emissions. But no liquid fuel goes here. And this is where fuel returns. So on early systems, we sent fuel from the gas tank up to the engine, and then any fuel that wasn't used would come back to the gas tank. And it would do this on a full tank of gas about every 20 minutes. It would cycle the entire content of the tank. So safety managed fuel tank can be positioned well away from heated components and outside the passenger compartment. That's new. We used to put fuel tanks in passenger compartments. Old pickup trucks, they were right behind the seat. You're sitting, basically your back was against it. A lot of passenger cars, Nissan, back in the 60s, 70s, put it behind the rear seat, between the rear seat and the trunk. And something as recent as a Jaguar, 1990s, still had it between the rear seat and the trunk. So gas tanks have been moved around quite a bit. Modern emission controls prevents tanks from being vented directly to the atmosphere. So this is our charcoal canister. Because my gas tank can't stay sealed. Because just like the gas can when I'm mowing the lawn, if I put it out in the sun, it would pooch out. And if I open it up, pressure would go out, hydrocarbons go in the atmosphere. And then when I close it up and then put it back in the garage and it gets cold, it would suck in. And we don't want our fuel tank doing that. We don't want our fuel tank to sometimes be a 10-gallon tank and sometimes be a 16-gallon tank. We want it to always be the correct size. So I have to have a way of relieving pressure without letting any of the hydrocarbons escape. Hydrocarbons are what make smog, they're pollution. So we have a charcoal canister. And the charcoal canister has activated charcoal. So this is the same activated charcoal I might use in an aquarium or other filtration system. And what it does is it grabs the hydrocarbons from the air, allows the air to pass through, but it holds the hydrocarbons in this activated charcoal. And then when the engine starts up, it allows it to pull fresh air in, grab the hydrocarbons from the activated charcoal, take them up to the engine and burn them. So we're not putting them in the atmosphere. Or when the car cools off and the fuel level is dropping, which would create a vacuum, guess what? We can pull air in from the outside and might grab some of those hydrocarbons and bring them back into the gas tank. So this system went into effect on some models in 1970 in California, required on all light duty vehicles in 1971. So this is one of our earlier emission control systems that we still have on cars today. Now you cannot have any liquid gasoline get to the activated charcoal because it will destroy the canister. It'll break it down. That's why we have the float valve or the liquid vapor separator right here. And if we have the float valve, the liquid vapor separator, if you top off the fuel tank, you can force gasoline past it, and then you've just ruined your canister. That's why they tell you not to top off your fuel tank. So the filler neck, here we have our filler neck. Our gas cap's going to seal on the filler neck. We also have a restrictor right here with this little flapper valve. This restrictor is designed so you cannot put leaded fuel in it that we haven't sold since the early 90s, but it also prevents you from putting diesel fuel in it, which also has a bigger nozzle than other fuels. So unleaded has a smaller diameter nozzle. So this is a restrictor right here. Many modern vehicles are required by the EPA to have a non-vented gas cap. All gasoline powered vehicles are, diesels are not, because diesel fuel is not volatile. Diesel fuel doesn't evaporate the same way. So diesel fuel does not have a fuel evaporation system or a charcoal canister and does not need a sealed gas cap. Prevents fuel vapors from being directly vented in the atmosphere. Many of these use a ratchet. Some newer Ford vehicles and other manufacturers have gotten rid of the gas cap altogether. So here we can see Ford's Easy Fuel. So this, you just put the nozzle in and take it out, it seals automatically. And here's just a standard fuel cap right here. Now, sometimes if the cap is not tightened all the way, or if the cap goes bad, the check engine light can come on. Most people, that's not an issue. They're able to tighten their gas cap, but occasionally you have someone with arthritis or who's older that has a hard time tightening the gas cap and keeps turning that light on. First, like the threaded gas caps and some other models they make in it's sold as a gas cap, but it basically converts it to this Ford Easy style system. So it's self-sealing. So you no longer need to take a gas cap off. when you go to get gas. You can just fill it up. So that's kind of a neat feature that is legal. Stamp makes them. I'm sure some other companies do also, but they are actually legal. They're not considered modifying your system for a purpose of smog. And because as I said, I've had customers, I've had elderly customers that literally they just can't tighten their gas cap enough to get it to seal anymore. And that's been a solution. So that is something that's available. When these go bad, and they do on the Ford system or the Chrysler system, or any of them that do this, you have to replace the entire filler neck. So instead of going and buying a $20 gas cap, you're buying a $300 filler neck and a couple hours to put it in. So it's a lot more expensive to replace when it does go bad, and they do. So our fuel pump relay works just like any other relay on the vehicle. We've learned about relays. So it's an electromagnetically operated switch that basically activates the fuel pump. So instead of running the power through the ignition switch to turn the fuel pump on, we use a relay, and we're going to turn the relay on either directly by the ignition switch or by the powertrain control module. A low amperage circuit is passed through the windings in the relay. A magnetic field is created, pulls the contacts together, controlling the larger current flow going to the fuel pump. So you can see here where you have your fuel pump relay. In this case, the PCM is going to turn it on. So we turn the key on and power goes what? It powers up the PCM. Now the PCM is awake. Oh, I need to turn the fuel pump on for 2 seconds. I just woke up, and that's why it comes on for 2 seconds. Then it's ready to turn it on more, but it has to wait to see the engine is going around. So it's going to be looking for the cam or crank sensors or both. Or distributor if it's an older car before it'll turn that fuel pump back on. And that's done for safety. That way, if you get in a wreck and your engine dies, your fuel pump's not going to be pumping all that gasoline out into the wreck site, which will obviously create a huge fire hazard. So that's why we have the PCM in control of that, is so the PCM has to see the engine rotating, that the engine is running, or it turns the fuel pump off. The current operating the fuel pump relay winding is typically controlled by the PCM. In most cases, the PCM grounds the winding when it wants the fuel pump to operate. So most of the time, the PCM or computers in general control the ground side of the circuit, and the power side of the circuit is supplied all the time to a relay or even an injector or something like that. Not always, there are exceptions, but the majority of the time, the PCM is going to control the ground side of the circuit, turns on and off. So our fuel pump, a couple different types of fuel pumps we use depending on the generation. Most common type we use today is a rotary vane pump. So they spin at fairly high speed, located inside the tank. Some transition vehicles from the 80s had electric fuel pumps on the frame rail and not in the tank. Those tended to be low pressure fuel systems. Electric pumps can be low pressure type or high pressure type, only fuel inside the pump, so there's no danger of explosion. This is designed to deliver more fuel than the maximum requirement of the engine. So fuel pumps that are mounted in the fuel tank are what we call a push pump. That means they're able to generate a great amount of pressure, 80 PSI, 90 PSI, but they have very little capacity of vacuum in order to be able to pull fuel into the pump. So they really rely on the weight of the fuel, pushing fuel into the pump, and then the pump is able to take that fuel, pressurize it, and send it out. So fuel also is what cools the pump, both because it's immersed in fuel all the way around, and the fuel is being pulled through the pump. This is why you don't want to run your car on less than a quarter of a tank. When you run less than a quarter of a tank, you put a lot more stress on your fuel pump. It's going to run hotter, which means it's going to last longer. It's also having to work harder because it doesn't have the weight of the fuel helping to push fuel into the pump. So it's working harder to try to pull that fuel into the pump and go. So at the same time it's working harder, it has less cooling. So it becomes exponential. And we do see, I mean, we replace a lot of fuel pumps. And What I can tell you, the one thing I see in common on people that replace fuel pumps is they tend to run their car on empty a lot. Is that to say it's a guarantee if you never run below a quarter to tank, your fuel pump will never go bad? No, of course not. But what I can tell you is your odds of having a fuel pump problem are substantially less. And, to replace a fuel pump on many modern vehicles is about $1,000. That's a pretty expensive repair. That's avoidable by going and getting gas more often. So I would really, recommend you not go below a quarter of a tank of fuel in your vehicle. So fuel pressure is controlled either by a pressure regulator that maintains fuel pressure between the pump and the injectors, or the speed of the pump is varied to maintain the correct pressure. So on older systems, the pump ran at full speed and we just bled back the fuel we didn't use. On newer systems, we actually will duty cycle or pulse width modulate the fuel pump, normally duty cycle, so that it's only getting 6 volts instead of 12 volts. So it's not rotating as fast, it's not making as much fuel. A pressure check valve maintains fuel pressure in the system after the engine shuts down. So when I turn the car off, it should maintain fuel pressure in the fuel system for a period of time, normally 30 to 60 minutes, and then it'll bleed off a little bit, but very, very gradually. Cars that have a long cranking time, one of the most common things that causes that is a bad check valve in the fuel pump. Because what's happened is it's allowed all the fuel to drain back to the tank. So now we have to fill everything back up with fuel and pressurize it before we can start the car. So that's where you get several seconds of cranking before the car starts on a fuel injected vehicle. Number one most common cause of that symptom is a bad check valve in the fuel pump. 3 different types of fuel pumps that the book talks about: the roller cell pump, a peripheral pump, and a side channel pump. And really, I don't care. It's nothing I'm ever going to test you on, because the reality is I don't get to call the parts store and say, I only want this type of pump design. I'm going to get the one they sell me or the one the dealer sells me for the vehicle I'm working on. And I normally only use dealer pumps. I don't use aftermarket fuel pumps, because they can design it differently inside and make it cheaper to sell it on the aftermarket. So generally fuel pumps, I only put in factory ones. But the book does go in and shows you some of the different types of pumps. Again, we're not cutting them open, we're not fixing them. I don't really care that much, but it's there. Our fuel tank send unit, we learned about this when we learned about rheostats. So this is a repeat. Sends a constant electrical signals to the gas gauge located in the driver information center or to the BCM. Well, it does that because it's a variable resistor. It's a rheostat. So it changes the current flow through the circuit, which changes the signal. Or in the case of a computer, there's a second resistor inside the computer, and it's changing the voltage on the wire between the internal resistor and our variable resistor in the sensor. This is what we call a fuel pump module. So our fuel pump is inside here. This is our screen for the fuel pump right here. Here's our level sensor right here. So here's our float, and here's our rheostat right here with the 2 wires going up to it. On today's electronically fuel injected vehicles, the send unit is incorporated in with the fuel pump. The entire assembly has 3 jobs: pick up fuel from the bottom of the tank by the way of the fuel pump, strain the fuel and pressurize it, and report the fuel level in the tank. Many manufacturers, if the send unit goes bad, you can buy them separately without having to buy a whole fuel pump module assembly. However, you will have to take it out to replace it normally. Not always, but many times. Nissan had a real big issue on their trucks. It was actually turning check engine lights on. And you could buy it. They had an updated level sensor, and you would pull it out, put the updated sensor in, and put it back in. You didn't have to buy the whole fuel pump. So here's our sock. These are good for the life of the fuel pump. Anytime we replace a fuel pump, we always want to replace not only the sock, but also the inline filter. So this is the first defense. This has a fairly coarse filtration, so it's designed to keep out sand and other large particles. It's not going to keep out very fine particles. It's just trying to prevent things that'll get into the pump and destroy the pump. Fuel lines made from metal tubing or other synthetic materials. We use some plastics or a combination of them. Carry fuel from the tank to the engine, and a return lane may also be provided to allow excessive fuel to return on older vehicles. Book spends a lot of time on return lines in the last 15 years. I can't think of anyone who's still using a return system. And we started getting rid of fuel return over 25 years ago. So the book treats this as very, very current. It's really not. We've moved past these systems in the last, they still have some in the late 90s. They've had fuel return systems, but nothing today does. Evaporative emission system lines connect the tank to the charcoal canister, and again can be made out of plastic. So you can see here we have a plastic line connected to a metal line. Many times there's special tools required for separating those. So here we look at our fuel filter. You can see here you would use 2 wrenches on this side, but you have a special tool you use to disconnect this side. So I have a whole drawer of special tools just for disconnecting different fuel lines, transmission cooler lines, and oil lines. I have a whole drawer dedicated to this. There's that many different ones. So our fuel filters, most vehicles today no longer have a serviceable fuel filter. It's in the fuel tank module and is replaced when the fuel tank's replaced. So it's kind of a lifetime filter. On a system like this filter originally were designed to be replaced every 30,000 miles. So when we first were using fuel injection filters, you're looking at 30,000 mile service interval. Then some of them went as long as 60,000 miles. These have a lot of material in them and a very high micron level. So these are filtering on the level that our oil filter is leveling. So 20 micron or potentially even smaller. These will plug up, but there's so much pressure behind them that they will generally still flow fuel. So you have a fuel pump, say my car needs 55 PSI to operate. My fuel pump's capable of 80, 90 PSI. So in order to get 55 PSI out, I might have 90 PSI going in. The car's still running okay, but the fuel pump's killing itself trying to do the job. So that's why anytime we replace a fuel pump, we always replace a fuel filter. The other thing is because when fuel pumps go bad, there's metal parts inside the fuel pump, and that metal gets sent into the fuel line, and that metal ends up in the fuel filter. So that's the other reason why anytime you replace a fuel pump, you replace the fuel filter. I also replace the fuel pump relay at the same time, because as fuel pumps go bad, many times they start to draw more current, which puts more stress on the relay, and I don't want the car coming back because the relay's bad. And relays are cheap, so I normally put a relay in at the same time. These are really not designed to trap water, although because of how they're mounted, they may, because water weighs more than gasoline. Most fuel filters are directional, typically found on the frame or somewhere underneath the vehicle. But you can see by eliminating something I have to replace every 30,000 miles, we've what? Lowered the cost of maintenance, lowered the cost of car ownership. So when we look at maintenance costs for cars, that's another reason why manufacturers are doing this, is because, right, we get graded on how much it costs per mile to own our car. So a lot of this stuff's gotten pushed out. The other thing that's really changed is that with modern vehicles, since we're not returning the fuel back to the tank and constantly cycling through, the fuel's only going through the fuel filter once instead of every 20 minutes. Our fuel rail is where the fuel injectors mount. So this is our fuel rail. So this is a reservoir of pressurized fuel. And here's my fuel injectors right here and right here. And so you can see 2 prongs. So a fuel injector is a solenoid, a power and a ground. This happens to be a multi-port fuel injection system because I have a fuel injector for each cylinder going into the port. And the computer is going to normally control the ground on the injector, and power will be supplied all the time. But our fuel rail is a reservoir, so that when we first dump on the gas and I need to put a lot of fuel in a hurry, I have enough fuel under pressure that I'm able to give it that initial squirt of gasoline, so my car accelerates while the fuel pump and while the system works to maintain that fuel pressure. So that way we don't have a restriction somewhere where I might have a performance issue. Fuel rails are usually sealed by flared ends, quick connect high pressure O-rings or banjo fittings. If it uses an O-ring or a banjo fitting, we want to make sure we replace the O-rings or replace the sealing washers on a banjo fitting every time it's taken apart. Failure to do so can result in a fuel leak, which can result in a catastrophic fire on the car. A Schrader valve uses a one-way valve to hold pressure in the system while the pressure tester is connected and disconnect the fuel rail. So some systems, predominantly domestic, have what looks like a tire Schrader valve in the case of Ford, or a different fitting on GM and Chrysler that allow you to hook a fuel gauge to it without taking the system apart. So that's something that's unique to domestic manufacturers. Is the fuel pressure in the fuel rail variable? Does it change? Yes, it does. It is going to change based on condition. And we see that especially on return style systems, which I'll probably be getting in, I know at this point I'll be getting into tomorrow. And it reached because I need more fuel pressure under higher load situations. So we will adjust fuel pressure based on load. So great question. So it will have change, and it's going to change in a fairly small range, normally a 10 psi range. So it doesn't change a lot. So it may go between 55 and 65 psi or between 30 and 40 psi, but it will change, and there is a specification that limits the amount of change I'm allowed. But certainly if I just dump open a whole bunch of injectors and put a whole bunch of fuel in, I'm going to have a slight pressure drop. I need to build that up. I need more pressure available when my foot's in it, going up a hill than I do coasting, because that way I can put more fuel in the engine in the same amount of time by raising the pressure. Does it change because the fuel pump changed the pressure in the tank or by some other mechanism? I'm going to get into this more when we get in return systems. So a couple different ways we can change it. One is I can use a fuel pressure regulator, which works kind of like your thumb over the end of a garden hose to change the pressure in the garden hose. So that's going to be basically a mechanical device. Some of those were built into fuel filters and other things. Other ones use a spring-loaded regulator that was mounted in the fuel pump module that just dumped it right back in the tank. Modern vehicles are actually changing the pump speed to change the amount of pressure that the pump is able to put out. And that's what we see as a modern strategy. Been doing it now for 20 years, but more and more manufacturers are doing that, where they're using a pressure sensor, and then they are varying the speed of the pump to hit the desired amount of pressure in the sensor. And a lot of these on newer vehicles don't vary that much, but so you're looking 5-10 degrees, and it will vary a little bit based on deceleration, acceleration, and so on. There's no reason to have something work as hard as it can. We only want it to work as hard as it needs to. And we'll get into more of that tomorrow, Branko.
Thank you.
So fuel rail. So here we can see a fuel rail. It's very similar to our brake lines, only bigger. This is the banjo fitting I was talking about, where it has a banjo bolt and it has 2 sealing washers, one here and one here. The mistake a lot of times people make is they lose this back sealing washer and don't realize it's supposed to be there. So they put it together and fuel goes everywhere when they first turn the key on. Or the other thing is they can't find a sealing washer, so they try to reuse them. And I know of a few cases where cars are burned to the ground from people doing that. So you never want to do that. You never want to reuse the sealing washers. I have drawers of just sealing washers so I can match up the right ones and put that. And I had that back when I had my shop. I still have them here in my shop at the house because it is that important to match them up. This is where I was talking about right here by disconnect. And in this case, this little plastic tab has to be pushed over the top of this little piece of metal, which is a ridge that goes all the way around the filter. So there's a tool that slides in the back side and pops this up and allows you to pull this off. Some of these also work where you can push in on the tab right here, has a fulcrum in the middle and lifts this up enough to come off. But many times they either don't work or they don't work like that, even though it looks like it might be one of those. So they do make tools that's very small that slide right underneath here and pop this up, and then you slide it off. And that's a typical fuel removal tool. And like I said, I have quite a few of them because there's a lot of different ones. But that is how we pull those off. So with this, I'm going to stop because the next section is fuel pressure regulation. And it's fairly big, and I don't want to get into it with 5 minutes to go.